Good morning. I'm Carlos Duarte and I'm the president of ASLO. And it is my pleasure today to introduce the recipient of the 2010 George Evelyn Hutchinson Award of ASLO. And the recipient of the award is Dr. Peter Dillon. And Dr. Peter Dillon clearly represents and portrays the traits and merits that are recognized with the Hutchinson Award. And the Hutchinson Award was established in 1982 to recognize excellence in limnology and oceanography and excellence in contributions to our science. Dr. Peter Dillon is a Canadian citizen and received his PhD from the University of Toronto under the supervision of Frank Riegler. He then moved on to work with the Ministry of Environment of Ontario, where he set up the Dorset Centre for Research that is dedicated to research on boreal lakes. And then he moved on to the University of Trent, where he is a professor at present. He has received many recognitions and is a fellow of the Royal Society of Canada and is also an associate professor to the Oxford University. He has authored many papers in the field of limnology, and one of his papers on the relationships between chlorophyll and phosphorus was the paradigm of an elegant paper that we should strive to when I was a grad student at McGill University. So I am very well aware of the research of Peter Dillon, as I believe everybody in the room is, and his research has spanned a broad range of topics in biogeochemistry of freshwater ecosystems, from eutrophication research to acidification of freshwater waters, and also the role of heavy metals in the environment and fluxes and biogeochemical fluxes of heavy metals and other compounds in the environment. So with this, I would like to invite Dr. Peter Dillon to join me on the podium to be presented with the award. So it is my great honor and pleasure to present Dr. Peter Dillon with the George Evelyn Hutchinson Award 2010, and I will read the citation that goes for his pioneering work in chemical limnology, introducing innovative research on eutrophication in lakes and long-term studies that have significantly advanced understanding of the responses of lakes and wetlands to acid deposition and climate change. So, congratulations.
Thanks very much, Carl. Well, thank you, Carlos, and good morning, everyone. Well, the first thing I'd like to say is that I'm extremely honored to receive the Hutchinson Award from a society that I first joined in my early years as a graduate student at the University of Toronto, and whose journal I have sitting on my shelves right back to volume 1, number 1. I'm not that old, though. I bought the first 20 years off another scientist who was retiring. No one receives awards like this without a lot of help over the course of their career, and I'm certainly no exception. And I like to spend my time here talking about some of the people who influenced my career. I'd also like to describe how the person who this award is named for, or at least how his writings influenced me. My early background as an undergraduate, a master's student, and initially a PhD student was in chemistry. Not environmental chemistry, but industrial chemistry. But when I looked into my future and saw a career with Dow Chemical or Domtar or maybe BP, close to the mic? Okay, sorry. It wasn't all that appealing to me, and I basically wanted to do something more exciting. At that time at the University of Toronto, there was no environmental science department. And what little environmental science there was done in either the zoology or the botany departments. So I got the university calendar, and this outlined the faculty and what all their research interests were. And I took my extensive knowledge of environmental science, which came basically from Scientific American and National Geographic specials, and I approached 4 or 5 of the faculty members to see if anyone had any interest in taking on a graduate student from a totally different background like mine. Oh, forgot my title slide here. They all expressed either little interest or, more often, no interest at all. That is, until I met Frank Rigler, who, to my surprise, got more and more excited as we talked, and within half an hour had asked me how soon I could start. Bottom line is, within 2 weeks, I was in a new department, had a new PhD project, and was on an exciting new career path. At that time, I had absolutely no idea who Frank Rigler was, of course. I came to Frank's lab totally ignorant of environmental science, particularly the biological part. My last course in biology had, in fact, been in my first year of high school. And he realized, as I did, that I needed a crash course in many things, particularly limnology, if I was going to become a limnologist. His method of getting me up to speed was very simple. This was in June, and he announced that in 2 months I would teach his senior and graduate limnology class in his place. So I looked around at the other grad students to see what limnology books I should have. And at the time in the lab there was Rob Peters and Dave Lane and Jim Haney and John Confer. And basically they all had the same core textbooks. When I started, there was no Wetzel, there was no Cole, no Horn, no Kelf. There was basically Rutner, and there was Hutchinson volumes 1 and 2. Volume 3 came out a couple of years later while I was still a student. Well, Rutner, oh, and by the way, the picture, I'm not sure which one is Rutner in that photo. These are limnologists at Lunds, Austria. Rutner's included there is Tienemann and Lund, 2 other very famous limnologists. Rutner was pretty straightforward, even for someone like me with absolutely no background. And I finished it pretty quickly. And I started in on Hutchinson, Volume 1. And of course, Hutchinson Volumes 1 and 2 are a lot different than Rutner, with Chapter 5 on hydromechanics and 140 plus equations, and in-depth chapters on thermal properties and optical properties. At the time, I shared a lab with Rob Peters, later of body size fame, which was not only a great learning experience, but an awful lot of fun as well. And one day Rob asked me how it was going, and I said, oh, okay. Parts of Hutchinson, though, were pretty tough sledding, and I was taking a while to get the hang of some of it. And he looked at me incredulously and said, what? You're not actually reading Hutchinson. Nobody reads Hutchinson. You just put it on your shelf because it's so thick and imposing and it looks so good there. Well, I persevered, though, and read the first 2 volumes in those early months. And Rob assured me I was the only person in the world who'd ever read them cover to cover. And he made a plaque to commemorate that. And now, those 2 volumes are where I did get my basic training in limnology. Many years later now, I still refer to Volume 1 on a fairly regular basis. The other volumes, maybe not so much. And the regular lab was also where I got my start in substance budgets, or as they're more commonly called now, mass balances and modeling, which has been the core of my research ever since. These were actually very exciting times in the regular lab. The great debate on empirical science versus mechanistic or reductionist science began then. Frank was already very well known, and a string of the greats in aquatic science passed through the lab in those days, and the students, including me, got to talk to them. Tommy Edmondson, Art Hasler, Joe Shapiro, Valdemar Oli, Hans Joachim Elster, Vittorio and Livia Tonoli, Ed Devey, Noel Hines, Willem Rhoda, and others all passed through the lab while I was a student. And of course, Richard Vollenweider, who had come to Canada just a year or two earlier to work just down the road from Toronto at the brand new Canada Centre for Inland Waters, which was where I ended up working after I finished my degree. I had the pleasure of working with Richard for a year and a half. It wasn't everything but name my postdoc. He worked for the government, and the government didn't have postdocs in those days, but basically that's what it was. Richard was a very educated man, able to work in 10 languages, and in his spare time he played Bach violin concertos and read Homer in the original Latin. He's best known, though, for his original relationship where he took lakes and put them on a plot of phosphorus loading versus mean depth, and found that in doing this, he could separate lakes into their trophic status categories: oligotrophic, mesotrophic, and eutrophic. This later went through a number of variations with hydrologic parameters added in, then sedimentation added in. But perhaps I think he should be better known for a paper that came out a year after these empirical relationships, a paper that I've put the reference at the bottom of this slide. This paper gave a very detailed development of a phosphorus mass budget model. But perhaps because it's in German, it hasn't been as well recognized as I think it should. But in many ways, it's really the foundation for substance budgets in the modeling of lakes. And it can be easily shown that all these empirical relationships actually derive very simply and directly from these mass balance models. Another fact that's not well recognized is that Vollenweider's relationships were, in fact, the first use of the critical load concept, a concept that later became the basis for the acid rain modeling that's been done and all the international emission control programs that have resulted. Models such as MAGIC, which this schematic represents, and that are used globally. This is the work of George Hornberger and my good friend Jack Cosby, are fundamentally mass balance models with a few processes overlying the mass balances. Another scientist who passed through the regular lab on a fairly regular basis was Dave Schindler. After meeting him for the first time, I wrote him, this was while I was still a student, and I brashly asked him to send me all of his data. I wanted to use it in developing some global models, including the phosphorus chlorophyll model that Carlos mentioned. Well, ELA was only about 10 years old at the time, but even 10 years of ELA data is a lot of data. And there were no PCs at the time, only photocopiers and pencils. A very reasonable response to my request would have been, "Are you out of your mind?" But Dave very generously told me that not only could I have everything, but he asked me how I wanted it organized. We've been friends for many years, and I've always been deeply impressed with his generosity, with his data, his ideas and his time. Dave perhaps didn't invent, but he certainly mastered the science of ecosystem manipulations. I've also been very fortunate in having a string of excellent collaborators, grad students, and postdocs. Lou Malott was one of the students who had the misfortune of being taught limnology by someone with 2 months' experience. Despite that, he and I have worked together almost continuously ever since. Now, I use the title of Substance Budgets, What Can We Learn from Them? And this has been the gist of what I've been doing in my research career for these many years. Why is it so useful to measure the flux of elements and substances in general in the environment? Originally, I think it was seen as a means of assessing the relative importance of different sources. At least that's the way it began with phosphorus. For example, at Gravenhurst Bay, which is very near the site of this month's G8 meeting, by the way, near Dorset, clearly was eutrophied by wastewater discharges. And once these were removed, water quality improved greatly. Things like this now appear self-evident, but budgets had a second important use. They let us, through modeling, quantify change, how much phosphorus concentration would decline, how this would affect chlorophyll quantitatively, how this would affect oxygen, and so on. In Lake Simcoe, on the other hand, this is the biggest lake in Ontario, in southern Ontario, at least outside of the Great Lakes, also with water quality problems. A careful budget indicates that the 6 waste treatment plants that empty into the lake contribute only about 7% of the total load. And spending multi-million dollars on upgrades and new technologies will have only a modest impact on the water quality. Substance budgets have been useful for a wide variety of elements and compounds, right down to the ultra-trace contaminants. For example, a detailed mercury budget for this lake demonstrated that atmospheric deposition directly on lake surfaces is often the major source of mercury in lakes. In this particular example, 60% of the total input falls directly on the surface of the lake. We can now measure substances very routinely in nanomolar and even picomolar quantities, in some cases femtomolar. It's making it possible to work with almost any element or compound. Mass balances of system compartments have also been very useful. For example, DeVito showed that, contrary to common belief, natural wetlands are not a good phosphorus sink, at least in boreal areas. Rather, they released in winter and in spring what they had stored in summer during the growing season. On average, these 5 different wetlands retain, within experimental error, 0 phosphorus. Similarly, they retain inorganic forms of nitrogen, the ammonium, the nitrate, but they release an equivalent amount of organic nitrogen, so that when we total it all up, nitrogen is basically in balance. What's going in is going out. In addition to their use in evaluating sources and as input to mass balance models that can be used for prediction, substance budgets have been important in another way. They've often given us surprising and valuable information about processes. When acid rain first became an area of concern, it was assumed that the ANC, the alkalinity in a lake, was produced within its catchment. That is, this was assumed until budgets were actually measured, at which point it became apparent that in acid-sensitive areas, particularly in the boreal region, most ANC was derived internally within the lake. In this particular case, for example, only about 20% of the alkalinity is actually produced by the lake's catchment. The other 80% is produced by internal processes. And how does this work? It works because redox processes are, in fact, an integral part of the ANC cycle. Any reduction produces alkalinity, any oxidation consumes alkalinity. However, in some cases, it was, sorry, go back one there. In some cases, it was apparent that the usual redox processes didn't produce enough alkalinity to make the budget balance. In this example, about half of the in-lake production comes from the sulfur and nitrogen cycle. And this told us that there were other processes that were important as well. And an even more careful budget demonstrated that a process not previously considered, and that is the photodegradation of organic carbon compounds, dissolved organic carbon, could generate as much acid neutralizing capacity as the sulfur and nitrogen cycle. One last example, carbon budgets. Carbon budgets not only verified that lakes in general are oversaturated with CO2 and are thus a significant greenhouse gas source. In fact, in amounts that are significant on a global scale in the global carbon budget. They also showed how the terrestrial produced carbon that comes into a lake as DOC and DOM is apportioned through in-lake processes, photooxidation, production of greenhouse gases being one, sedimentation being the other, into these two routes. And comparison of carbon budgets from multiple lake systems demonstrated that the acidity levels in lakes control this proportionation between releases greenhouse gases back to the atmosphere and storage as a permanent sink in the lake sediments. I'd like to summarize with one final slide that gives a couple of the core lessons I think I've learned over the years. The first of these, if you really want to understand a lake, you can't do it without studying its catchment as well. They are so intimately linked that they must be treated as a unit. The second is that concentrations are good, compartment and pool sizes, okay, but if you want to understand fully, you need to also measure and understand fluxes. You need to understand the rates that substances are moving through the environment. And finally, and perhaps most important, I would like to emphasize the value of long-term data, substance budget data in this particular instance. And it's incredible use in assessing environmental change. And these data sets must not be compromised. The Hubbard Brooks of the world with their 50-plus years of data, ELA with over 40, even Dorset, where I've worked, is now in its 35th year. These are the data that are going to play a major role in determining what climate change is really doing to the environment. Thanks very much for your attention.